Hello everyone, I'm Jesse Lurkley, and today I'm talking about my paper Fast Community Detection with Graph Sparsification. So the overall research question I'm interested in is how much does inaccuracy impact machine learning computations? And this is something that's sort of well understood in physics, that there's many places in a physics simulation you can compute inaccurately and still end up with a very accurate final result. And practitioners of machine learning are also aware that there's many times in machine learning where you can compute inaccurately and still end up with a very accurate algorithm in the end. So I'm interested in quantifying that and sort of rigorously showing where that's possible. So that question is much too broad. In this talk, I'm going to look at just the example of clustering. And clustering is also too broad. I'm going to look at just clustering using spectral methods. So spectral clustering is based on the idea that you take the matrix representation of a graph, you compute a particular eigenvector of that matrix, and that eigenvector has all the clustering information embedded in it. And there's a couple of different sort of ways we could introduce inaccuracy into this. We could drop elements of our matrix, and this is very attractive because if you have a sparser matrix, the computation is much faster. So for example, if I use a nearly linear time solver to compute my eigenvectors, and I drop one order of magnitude of the edges, my final computation for the eigenvector will be an order of magnitude faster. So that's very attractive. On the other hand, we could also compute the eigenvector inaccurately. So instead of doing 10 to the 8th or 10 to the 16, we could compute 10 to the minus 1. So how does that impact our clustering? So even the question of how do these forms of inaccuracy impact spectral clustering is too hard. For a general graph, we have to fix a particular model. So we're going to start with this stochastic block model. And stochastic block models have a particular number of communities. Here I'm working with a 2-community stochastic block model, and the parameters are you have some probability of an edge between nodes inside a community and some probability of a connection between nodes that are not in the same community. And you might say this model is too primitive to be useful, but actually, aside from being an interesting building block toward higher, more powerful community models, it can also serve as a basis for an actual clustering algorithm because you can apply this algorithm recursively, get 2 communities, and recur on those communities until you find what you're interested in. So this actually has some practical value aside from being a building block. All right. So the first step for our algorithm would be to recover the parameters of this model, the p, the probability of a link inside a community, and the probability of a link between nodes that are not in the same community. And if you're interested in 2-community stochastic block models, there's a linear time algorithm that can return you these parameters. And the theory tells us that if our p and q are such that this inequality holds, then the communities can be recovered, and if that's not the case, then they cannot be. So that will be an important criteria for designing our algorithms. The theory also has a lot to say about what the spectrum, what the eigenvalues of the matrix of these models looks like. So we have one eigenvalue that's associated with the eigenvector with the clustering information, and then the rest of the eigenvalues are distributed according to this semicircle law. So this will be quite useful later on. Alright, so we had 2 approaches. We were going to introduce error, and one of those approaches is sparsification. So we're going to drop edges. So a natural way to sparsify would be to sparsify by effective resistance, because there's the hope that edges that are between communities would be dropped before edges that are sort of inside communities. And unfortunately, it turns out that as graphs get bigger, the ability of effective resistance to encode any useful information about graph structure goes away entirely. So you're basically just sampling randomly if you use this method. But that's all right. We can start with that. And our approach is we can compute the expected value of P and Q if we know the original P and Q and we know how many samples we're going to do. So you do that number of samples, you compute your P, you estimate what your P and Q will be, and then you plug that into the equation earlier and see if you're able to recover the communities or not. And if you are, then you don't need any more samples, but if you are not, then you need a higher number of samples. So this is a very crude method, but we'll see in our results that it does work and it's relatively easy to do. On the other hand, really it would be nice to make use of some of the community structure when we're dropping edges, and you can do that by sort of correcting your effective resistance. So there's lots of different methods for trying to correct effective resistance. One of them is to scale it by the degree of each node, and then all the effective resistances are going to be around 2. So you're then interested in the variance around 2 of each edge. So it turns out you're able to show what the effective resistance of an edge on average is inside a community and what the effective resistance is on average outside a community. And you can then compute the ratio between those, and that helps you if you're going to sample by these scaled effective resistances. You know sort of what the ratio is that you'll sample inside versus you'll sample outside. So based on that, we can now get a new expected value for our P and Q based on this scaled effective resistance, and it turns out your expected value, your expected number of samples to get a P and Q such that you can recover the communities is much lower if you use the scaled effective resistance. So that's a nice result. All right, so moving on, there's the other method, which is to compute the eigenvectors inaccurately. So instead of computing to 10 to the minus 16 or 10 to the minus 8, we'll compute to 10 to the minus 1 accuracy or something like that. So how do we know when to stop? So the first thing to do is we have to pick an eigensolver, and we're going to pick inverse power iteration. And the reason we're going to do this is because the power method works well with these linear time solvers, and these linear time solvers work really well if we drop a lot of edges. So we get sort of crossover between our two approaches. So the main approach here is we know the structure of our dominant eigenvector, the eigenvector that has the information we're interested in, and we know that the rest of the eigenvectors are basically have components that are normal random variables. And so when we do the power method, we've got a summation of our actual eigenvector that we're interested in and the sum of these random variables. And the sum of the random variables are scaled by some combination of the eigenvalues which we know from the theory. So remember, we recovered the parameters of our community. We can plug that into the theory and get the distribution of the spectrum. So we know what the contribution from the random elements are distributed according to this normal variable. So then we just go ahead and apply Chebyshev's inequality, and that will tell us when our sort of the summation of all our eigenvectors of the summation of the random eigenvectors is going to be smaller than the actual size of the signal that we're interested in. So that's going to be after a certain number k iterations. All right. So the other point we make in this paper is that again, we want to use these linear time solvers, but a lot of times when you're doing clustering, you don't want to work on the graph. You want to work on the regularized graph Laplacian, but you still want to use these linear time solvers. So we're able to show that based on a common regularization method, if you go ahead and apply sort of a Sherman-Morrison approach, you can still split up the sum of your matrices in such a way that you can still use the linear time solvers. All right, so a couple of quick words on our results. So you can see that on a synthetic graph, so we generated a couple of many different random stochastic block models, and just one example, and we applied the inverse power method, and to get to the 10 to the 8th, which is relatively low accuracy, took 102 iterations, but to use sort of our stopping criteria took 12 iterations. And then here's some timings in MATLAB. Obviously, if you did a distributed computing or even a C implementation, this would be much slower, but it gives you a flavor of the expected time saving, which is significant. And here is a look at the accuracy. So down here we have percentage sparsification. Here we have dropping by the effective resistance, so essentially randomly. Here we have by the scaled effective resistance. So this is what the theory predicts we should get in terms of accuracy, and the line below is what we actually get. So you see that the line follows our predictions pretty closely, especially when we go for scaled effective resistance. And you can see that we're dropping quite a lot of edges, especially for the scaled effective resistance. So if you're using a linear solver, this is a pretty significant, nearly linear time solver, this is a pretty significant speed up. So here's a real world example. This often appears in the literature. You have a political blog. You're trying to predict which ones are Republican and which ones are Democratic. This is not exactly a stochastic block model, but it's close. So here you can see what we actually did, and here's what the theory predicts. And you can see that follows relatively closely for this real world example. Again, this is not exactly a stochastic block model, but we're pretty close. This line over here is when we predict that the graph will be connected. So the fact that we're actually able to find two communities at all is before this point is fairly good luck. All right, so that's the general overview. Is that we've basically analyzed for two community stochastic block models. Our results are pretty strong for that. We'd like to move on to sort of more heterogeneous, more multi-sized communities. We'd like to look at stronger models, and we'd like to look at more real-world data sets and implementation. So we'd like to look at whether at cybersecurity data, at other domains, and see whether these data sets follow stochastic block models, or if we need to employ more powerful models for this sort of approach to work. All right, thank you.